All right, let's go over Gibbs free energy and go through example number 3. So there's two main ideas for Gibbs free energy. Remember, Gibbs free energy is delta G. It's just G because Gibbs is the American scientist who studied it. Idea number 1 that's extremely important says there are two thermodynamic driving forces for any process. And those thermodynamic driving forces meaning that it will drive a reaction forward or backwards. Right, the first one is that there has to be a decrease in enthalpy, so enthalpy delta H has to be negative, that's the more favorable condition. And there has to be an increase in entropy, so delta S has to be positive. That's the more favorable condition. So when we have exothermic reactions, negative H, or more chaos, positive S, it will be thermodynamically favorable. I'm going to go ahead and write that. So when these two conditions are met, it will be thermodynamically favorable. The other word synonym that you might use is spontaneous. So if those two conditions are met, it's thermodynamically favorable. Things like to do that. It is spontaneous. It will happen on its own. We don't need to create any sort of special conditions for it to happen. However, if those two processes are not met, then it is called thermodynamically unfavorable or non-spontaneous. So when a process is non-spontaneous in the forward direction, it is spontaneous in the reverse direction. That makes sense? So if it doesn't like to go forward, it will automatically go in the reverse direction. A non-spontaneous process might happen when coupled with another spontaneous process. We'll go over what that means. And then third, while a process may be spontaneous, it may be very, 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 very slow, right? So for example, resting. Resting is a spontaneous process. Resting occurs on its own. We don't need to help it out, but is an extremely slow process. All right. Gibbs free energy, delta G, is defined as the following equation. We have delta G equals delta H minus the temperature, which is T, times the change in entropy, delta S. It represents the energy available to do work, and it has units of kilojoules per mole. The free energy of formation, which is the standard G, right? So the degree sign means standard, so it's the change of Gibbs free energy of formation, the little f, at standard state, is the free energy given for 1 mole of the substance. Whereas free energy of the reaction, is represented by Rxn, represents how the free energy of the system is changing in the process. There we go. So delta G of the reaction, the free energy of the reaction, helps us determine the spontaneity, so how spontaneous it is, does it go without any help, of the ambiguous cases. So, for example, processes in which enthalpy and entropy are either both increasing or both decreasing, that's spontaneous, right? Because we want enthalpy to decrease and we want entropy to increase, but if they're both increasing or both decreasing, it might be spontaneous, it might not be spontaneous. It depends on how much they're changing by. So that's when that can help us with that. A reaction is a spontaneous when Gibbs free energy is negative, and it is non-spontaneous when it is positive. So we want Gibbs free energy overall to be negative, and if it is non-spontaneous, it will overall be positive. Note that T is in Kelvin, not Celsius. Delta G and delta H are usually given in kilojoules per mole, but delta S or entropy is usually given in joules. So make sure before you add and subtract and plug that into this equation that they're both in kilojoules or they're both in joules before you add, multiply, and subtract and stuff like that. It tends to be easier to convert all of them into kilojoules than into joules, just as a experience. When delta H, let's fill in the table on the right-hand side, it says when delta H is negative, that means it's exothermic, right? That's favorable. And delta S entropy is positive. It is chaos, right? That's favorable as well. And then the process overall has to be a negative spontaneous. So delta G will be negative, and it is spontaneous. Right? It is favorable. When delta H or enthalpy is positive, that means it's endothermic. We don't like it when it's endothermic. And delta H is negative, so it's becoming more ordered. which is not favored either. Ordered, there we go. Then delta G will be positive overall. It is non-spontaneous. And I can't fit the word spontaneous in there, but you can write it yourself. So delta G will be positive. It is non-spontaneous. When they are both negative, right, if we plug this into our equation up here, if delta H is negative and we have a delta S that is also negative, so we have negative delta H subtracted by the temperature, we have a negative delta S. So negative times a negative right here is positive, but if the temperature is low enough, that means that we have a bigger negative H right here. And so if it will be spontaneous at low temperatures only. But if that temperature is too big, then it will be non-spontaneous, right? Because then this negative times negative is a bigger positive, and therefore it will be a positive delta G non-spontaneous. Likewise, when, I'm going to go ahead and erase that. Okay, it won't let me erase that. When they are both positive, so delta H is positive, subtract, we have temperature, and we have delta S is positive, right? Positive times a negative is overall negative. If we want delta G to be negative, that means we need that temperature to be a bigger number. So when we multiply those two together, it's a bigger overall number right here than that delta H. And so for positive, positive, it's spontaneous at high temperatures only. If it's at a low temperature, it's non-spontaneous. All right, idea number 2 says that Gibbs free energy is a state function, and so it depends on only the initial and final conditions, not on the process. So initial and final conditions, not on the process. The value of delta G can be found in the following ways. And these are the 3 following ways. We have delta G equals delta H minus T times delta S. We have products minus reactants, and we have Hess's law. These 2 right here, you should hopefully know how to do. This one right here is new, but it's super easy. Just plug it in, multiply, and subtract. So for example number 3, I'm going to actually start this on a new video just to make sure this is a little bit shorter of a video. Don't want to make it too long.